Section 8.4, multiply and divide rational expressions. We're going to get away a little bit from the graphing side of things and spend some time looking at simplifying some rational equations and expressions here. Actually, just expressions today. We'll talk about solving rational equations later on here in the next couple sections. So this should be primarily a review for us. We're going to be reviewing some factoring, dealing with what do we do when we're dividing polynomials, multiplying, thinking about canceling factors. So here we have the process by which we're going to be doing this. If we can create the factored form of polynomials in the numerator and the denominator for our rational expressions, then we are able to hopefully find common factors that we are able to cancel. So there are some examples here of what's going on with that. So let's try some of this. Factoring both and then dividing out the common factors is what we're doing. So we're not solving, we're just simplifying, changing the way that it looks. So I hope that this is review for most of us. X squared minus 8x plus 16 is going to become an x to the 4, x minus 4, x minus 4, or x minus 4 quantity squared. And x squared plus 2x minus 24 becomes an x plus a 6 times an x minus a 4. And here we see those two factors of x minus 4 canceling, and then just giving us the binomial of x minus 4 over x plus 6. Now, before we go on to the next one, let's back up a little bit and just talk about some things that maybe seem obvious, but I see the mistake happen often. When we are set up in expanded form, both of these are expanded forms. Sometimes it gets really tempting to notice that I've got an x squared on the top and an x squared on the bottom, and so that must mean I'm able to do that. And then maybe even some people even go further. Negative 8 and 2, they can reduce. But remember, you've got terms here. You've got three terms. You've got plus or minus going on. None of those are factors, and we can't simplify or cancel things unless we have factored form. So that's why we need to change our form from expanded into factored form. So don't be doing what we did over here. That's a no-no. Put it in factored form, then you can find things that are in common, then you can cancel them. All right, let's try this next one here. Move everything around. All right, for B, we have x plus 5 and an x plus a 2. Down in the denominator, we have a difference of 2 squares. And here we get x plus 2's to cancel. And again, binomial over binomial. C. A little different in the sense that we only have a monomial in the top term, or the top variable, top polynomial. And can't do anything in terms of factoring there. But in the denominator, we definitely have a GCF that we can pull out. So a 3x squared can be factored out. And 3x squared out of a 2x out of a 6x squared becomes just a 2. And a 3x squared out of a 9x cubed becomes a 9 or a 3x. And then we get that monomial term canceling with this coefficient, which is also the same thing. And then here's another classic mistake if somebody would just write either 2 plus 3x, or maybe even make this 0. But remember, when you cancel the 3x squared, it leaves a 1. You have a 1 plus, or 1 over 2 plus 3x. So there we are doing some factoring, simplifying, and we're going to carry that into the multiplying of rational expressions. The rule for multiplying rational expressions is the same as the rule for multiplying numerical fractions. You multiply the numerators, you multiply the denominators, and you write the new fraction in simplified form. Here they give some examples here. So let's go try some of this, highlighting a few areas of possible possible concern. So approaching it from the standpoint of, let's say I was simply going to go and start cross-canceling here, because I have a factor times a factor, which means I can go ahead and cancel things that are the same in the numerator and the denominator. So the danger in that, if you do that here, and you start working with, let's work with the coefficients first. You might say a 5 can reduce into a 15 and become a 3, and a 3 can reduce the 27 into a 9, and then the 3 can reduce that 9 to a 3. So I know I have a 3 now in the numerator. Then maybe we start working with the x's. We have an x squared over an x to the first. So this x to the first actually cancels out, and this becomes x to the first. Y to the third over y to the fourth is y to the negative first. If I made it positive, it would be a down in the denominator. So that goes away, and again, makes that 1. X to the fifth over x to the fourth becomes x to the first. And then there's just a y down there. So this gets kind of messy, and you might lose some of the problems you were working with. You might lose like powers, or maybe you'll lose coefficients or something. So if I'm doing this and I'm careful, I'm going to get a 3x squared on the top, and then a y squared on the bottom. Another way to do it is instead to multiply all the numerators together. So 5 times 27, you have 135. X to the second times x to the fifth is x to the seventh. And then y cubed. That's all the numerator multiplying together. And down in the denominator, 3 times 15 is 45. And x times x to the fourth is x to the fifth. And y to the fourth times y is y to the fifth. Now, it's not going to be so messy when we start to cancel things. So now we apply our properties of exponents. 135 divided by 45 becomes the 3. The x to the fifth and the x to the seventh becomes x squared in the top. And y to the third over y to the fifth becomes y squared in the numerator denominator, and we get that. So it might be better just to kind of save yourself from some silly mistakes to multiply numerators together as one big chunk. Do the same thing for the denominators, and then simplify from there. All right, here, I'm going to pull out a 2x and have a 2 plus x plus a 2 left over. And the denominator, I'll have an x minus 6, x plus 2. And then in the second rational expression, I'll have an x minus a 6, and an x minus a 3, all over a 2x. Okay, I can go ahead and start canceling. X minus 6's, x plus 2's, 2x, 2x, leaving me with just x minus 3 for that one. Let's try this one. I'm going to pull a 5x out. We're left with a 4 minus an x. Here I can factor out a GCF of an x. We're left with x minus 1 for the denominator. X minus 4, or x plus 4, and x minus 1 over the difference of squares. X minus 4, x plus 4. All right, now this one's good to take a peek at. Let's go with what we can cancel so far. So x minus 1 factor x minus 1. And then x plus 4 and x plus 4. And then oftentimes, these are the ones that are forgotten. We have 5x and then just a single x. So that means those x's get to cancel each other out. And for right now, we're going to stop and just look at what I have left. I have a 5 times a 4 minus x all over an x minus 4. Don't need to put parentheses around that denominator. I'm just using that to help demonstrate something here. All right, so if I look at 4 minus x, x minus 4, how are they related? They're related somehow. They are what we call opposites. I look at the numerical part, I have a positive 4 and a negative 4. And if I look at the variable part, I have a negative x and a positive x. That's what's making them opposites. And therefore, if I were to take the 4 minus x and factor out of it a negative 1, then I'm going to get 4 minus an x, and it's going to become, a negative comes out of it, I get a negative 4 plus an x, or negative 1 times x minus 4. Well, now I have the same factor. 4 minus x becomes negative 1 times x minus 4. And that means here I can make this become negative 5 on the top times x minus 4 over x minus 4 on the bottom. And I'm able now to cancel the x minus 4 factors. And then this whole thing just equals negative 5. So beware of opposites. Opposite variable, opposite constant, pull out a negative, and reduce from there. All right, on this one, I have a rational expression multiplied by a trinomial over there. So that trinomial actually has a 1 underneath it. But what's interesting about this one is the x minus 4 can't do anything with, but hopefully you remember that difference in sums of cubes. So x cubed plus 8 is a sum of 2 cubes, which makes it break down into x plus 2, x squared minus 2x plus 4. And then that whole thing, so all of this, is getting multiplied by this x squared minus 2x plus 4 in the numerator. Well, those two get to cancel each other out. And then I'm just left with x minus 4 and an x plus a 2. So beware of some difference of cubes. We're going to kind of see a little bit of everything that we've been working with when we were doing our review chapter at the very beginning. What about dividing rational expressions? To divide one rational expression by another, you multiply the first rational expression by the reciprocal of the second rational expression. Now we have a little saying that we use to remember that. It's called save it, change it, and flip it. What that means is just what that statement said. Save the first rational expression. Change the division symbol to multiplication, and flip the second rational expression. And so what that would look like for us here is it is x squared minus 4x minus 21 and 5x plus 15. There's the save it part. And now we change, and now we flip. And the reason we're doing this is because when you divide something, you multiply by a reciprocal. That's what division is. All right, and then now we're ready to factor everything. So we're going to get x minus 7x plus 3. And here I'm going to pull out a 5 and get an x plus a 3. Here's the difference of 2 squares. And here I get an x plus a 10 and an x minus a 7. And now we're ready to start canceling. X plus 3 factor, x plus 3, x minus 7, x plus minus 7, x plus 10, x plus 10, and this reduces to just x minus 10 all over 5. Now anytime you have something divided by a single term, I could separate that into 2 fraction pieces, and this could become x over 5 minus 2. So those are equivalent, they just are a different way of representing. All right, so we move on here through this, and again, practice our save it, change it, flip it. And that's going to become those get to cancel. And then lastly here, I'm going to go ahead and factor from on the fly. X squared is 3x and 9 all over negative 2x squared. Flipping, now this is an x squared plus 3x plus 9, so it becomes, when I change it to multiplication, 1 over, and then I'll go ahead and factor x squared plus 3x plus 9 is not factorable, so we're going to leave it, but that's nice because it happens to be one of the factors of the sum, or just difference of cubes there for x cubed minus 27. So then, 1 times x minus 3 over negative 2x squared. And I can't do anything with that x squared on the bottom and the x on the top because the x on the top is not a factor. So I'm just leaving my answer written like that. So again, it's been nice, a little bit of review on factoring. Let's take some application to this then. This might again cause us to have to go back and review a little bit in regards to some shapes and areas, volume. So here we have our cylinder. And a company is going to make 2 containers that have the same base. So you can talk about the fact that this part of the shape of the cylinder is going to be the same between the 2 cylinders. And each of those cylinders has a radius, and each of those cylinders has a height. All right, style 1 is going to have a height that is equivalent to the radius. Okay, so for our style 1, we know that h is going to equal r. For style 2, the height is twice the radius. So now our h is equal to 2r. Same base, just making it twice as tall. So what does that do then to volumes? And what does that do to the surface area? Surface area is the amount of material needed to make the cylinder, assuming we have a top and a bottom and then a round part. Volume is how much stuff we can put into it. So when I change the height this way, what's that going to do to volume? What's that going to do to surface area? Surface area and volume of a cylinder. Let's talk about those. Let's talk about the surface area first. If I took a cylinder and I broke it into pieces, the top and the bottom of the cylinder are those are both circles. And then if I took the height portion between the 2 circles and I unwrapped it, imagine like taking a can and cutting a can along the side vertically down from the top of the can to the bottom of the can, and then unfolding what you've cut, you have a rectangle. And so what happens is the height of that rectangle is the same thing as the height of the cylinder. But interesting here is that the circumference of our circle, once I unfold that can, becomes the base or the length of our rectangle. And so what that means is for surface area, which is add up all the area parts, we have 2 pi r squareds and a 2 pi r, there's the base of the rectangle, times the height of the rectangle. So that is the surface area of a cylinder, 2 pi r squared plus 2 pi r. What about the volume? The volume is taking the shape of the base and multiplying it by the height. So here, we just imagine a bunch of those little circular discs, stacking them up. You know, we're kind of ignoring thickness here. Volume would be equal to pi r squared times the height. Okay, if that's the case, then we could take these, and for style 1 and style 2, we can find their respective surface areas and volumes. So first, let's talk about style 1. Its surface area would be equal to 2 pi r squared plus 2 pi r and h. but our h, remember, is equal to r. So really, it's times r. So our surface area is now 2 pi r squared plus 2 pi r squared, which is 4 pi r squared. So there's the surface area of cylinder 1. This down a little bit. What about the volume for that? The volume is equal to pi r squared h, but our h became an r. So now we have r squared times r, or now pi r cubed. So there's our volume for style 1. For style 2, we have that the surface area is equal to 2 pi r squared plus 2 pi r. But now our h is twice the radius. So we have 2 pi r squareds plus 4 pi r squareds. Which simplifies to 6 pi r squareds, surface area-wise. And the volume is going to become pi r squared h, but our h is now 2r, so our volume becomes pi 2 pi r cubes. All right, so now we're going to see kind of some comparisons between these two. So the second part of this is to calculate the ratio of surface area to volume for each of the cylinders. So for our style 1, our ratio of surface area to volume would be 4 pi r squared to pi r cubed. And here we have a rational expression that can simplify, and we get 4 over r. For style 2, our surface area to volume ratio would be 6 pi r squareds over 2 pi r cubes. And this becomes 3 over r. All right, so those are our ratios of surface area to volume. From that, getting an idea of what happens here with our surface area to volume ratio, we can answer, hopefully, this last part. What do the ratios tell you about the efficiencies of the two canisters? So in regards to efficiencies, you're a company, you're producing this container, you want to minimize your surface area, but maintain a maximum volume. So use less material. So how do we use our ratio of surface area to volume to determine that? Well, since, for style 1, since 4 over r ratio is bigger than a 3 over r ratio, that would mean the style 1 is less efficient than style 2, because you're having a bigger discrepancy between your surface area and your radius here. So style 1 is less efficient. Than style 2, because it has a larger surface area to volume ratio. Let's go ahead and make our height twice as big as our radius, and we will be more efficient in the production of our containers. So there we go.